Hello everyone. Today we will start with new chapter, that is third module, which deals with flexural strength of PSC structures. What is flexural strength? It is nothing but it is a bending strength of the PSC member. So same as in case of RCC, we are going to find out what is the flexural strength of the PSC member. In this module, we have what are the different failure modes of the flexural members, then what are the design parameters we have, how to calculate the flexural strength or ultimate moment resistance of the flexural strength, then type 1 design of flexural member. In PSC we have three types of flexural members, so among three types we have only type 1 design. So in PSC we carry out the design with two different steps. One is preliminary design, then pre-stressing design. In preliminary design we are going to find out what is the cross section of the member required, what is the length, what is the span, and or what is the width of the beam, what is the depth of the beam. These things we are going to calculate. Then in second part we are going to analyze the section, then by analysis result we are going to design what is the pre-stressing force we need to induce and what is the cable profile, all those things. So first let us start with flexural strength or bending strength, we can say. So in PSC beam we have some parameters which affect the PSC strength of PSC members, that is flexural strength of PSC members. So the main factors which the flexural strength of PSC members depend are: one is percentage of reinforcement in the section, then degree of bond between tendons and concrete, compressive strength of concrete, and ultimate tensile strength of the tendons. So first one, percentage of reinforcement in the section. So same as in case of RCC, there should be minimum percentage of the steel we need to provide. Minimum will be there as well as maximum will be there. So while calculating, we used to calculate minimum reinforcement of 0.12% in case of RCC. So here we will be a little bit different, we'll discuss it later. And also maximum reinforcement 0.2% or 0.25% in RCC. So it should not be over reinforced or it should not be under reinforced. We need to maintain it as a balanced section, that is percentage of reinforcement. Then degree of bond between tendons and concrete. This comes in case of post tensioned beams. So what is the strength of bond between tendon what you have provided and the grouting arrangement what you have provided? What is the strength of grout you are implementing in the post tensioned beam? Those things will be depend. Then compressive strength of concrete, or it is, you can say, characteristic strength of concrete. Ultimate tensile strength of the tendons. What is the maximum tensile strength of the tendons and what is the pre-stressing force you are applied on the tendons? These things will be affect the flexural strength of the beam. So based on these factors, we are going to specify few modes of failure. In what modes the flexural member may get failure. So in that we have 6 different types of modes of failure. One is fracture of steel, then failure of under reinforced section, failure of over reinforced section, shear failure, failure of bond between the steel and surrounding concrete, and last one is anchorage failure. Let's discuss one by one. So first one is fracture of steel. So fracture of steel in tension. See, we have concrete as well as steel in the beam. So when you go on applying the loads, it will get deflection. So as the deflection increases, the concrete will get crack in the tension zone. So when you have provided the steel which is less than the required amount of steel. So for example, if there is a requirement of around 1000 mm square of steel, but we have provided around 600 or 700 mm square, so then it will not meet the tensile strength of the beam. So in that case, when the beam gets deflection, the concrete gets cracked and it will transfer the tensile stresses developed in the concrete to steel what you have provided, but it is not able to carry the loads or carry the stresses, so suddenly it breakdowns. So that is fracture. That breakdown we call it as fracture. So because of that fracture, the beam will collapse. That is the fracture of steel in tension due to excess of tensile stresses developed or transferred from concrete to steel. So in keeping this in mind, IS code gives us guidelines. If you are providing steel in PSC members, the minimum longitudinal reinforcement or main reinforcement what we are going to provide in a beam should be of 0.02% of 0.2% of cross section of the beam. If you have providing high yield strength deformed bars or high strength steel, then it is 0.15% of cross section of the beam is enough. So that is minimum reinforcement to be provided. How we are going to calculate 0.12% of cross section in RCC? Similarly, here we are going to provide 0.2%. If we are using high strength steel, it is 0.15%. So next one is failure of under reinforced section. So here AST minimum, we know there is a guideline for minimum steel. So that minimum steel gives for balanced section, percentage of steel required for balanced section. As in discussed in previous mode, we have 0.2%. It is a minimum steel we need to provide for any section. But as per the analysis, the loads coming over it is enough for less than 0.2%. For example, if we consider 0.2% means we need to give around 2000 mm square of steel, but as per the analysis we will get around 1500 mm square of steel. So that 1500 mm square is enough to carry the loads, but as per the guidelines we need to provide 2000 mm square. Minimum steel is 2000 mm square that you need to provide, but if you provide 1500 mm square, then that will become under reinforced section. So in this case the beam will get more deflection and the steel will give more elongation. The same elongation leads to more deflection. As the deflection increases in the tension zone, the concrete in the compression zone get crushes. So as the tension zone extends, the compression zone contracts. So that means because of that contraction, the concrete in the compression zone will get crushed. So by that the concrete will loses its strength and the neutral axis shift towards the compression side. So when compressive zone failures, the deflection again further increases, then at certain point the beam will get failure. So under reinforced section, how to decide means it will give larger deflections and wider cracks. As the deflection increases, the tension zone, the cracks will develop and the cracks will penetrate towards the compression zone. You can observe in the figure, at bottom we have cracks developed in the tension zone, and at top we have concrete crushed in the compression zone. Next one is failure of over reinforced sections. If we take this previous example itself, the steel required is 2000 mm square, but we think that okay, we need to give more safety for the beam, we will provide around 3000 mm square. So that is, the required steel is 2000 mm square is enough, but we are providing 3000 mm square by keeping safety in the mind. But that is not correct, because the section should be balanced. The compressive stress and tensile stresses in the section should be balanced. So when you give the steel more than required steel, too much more than the required steel, then it will become over reinforced section. So in this case, the concrete will get crushes in the compression zone. There will be no deflection at all, or very small deflection will be there, and very narrow cracks will get developed. Then the area of steel is large when compared to area of steel required for balanced section. The stresses developed in the stages may not reach the tensile strength of the steel. So concrete will have certain strength and steel will have some strength. When both should meet, then your beam will be in stable condition. But the concrete fails before the steel come under its extreme stresses or come under its capacity. So in that case, the beam will fail suddenly. That is, sudden failure will be there. There will be no warnings like excessive deflections or cracks developed in the beam. There will not be any warnings. It will failure suddenly, because of the concrete will not allow the steel to take its extreme stresses. That means the steel will not take the stresses to its extreme capacity. If the steel is able to take a load of 100 kilonewton, the concrete will not be ready to give that 100 kilonewton for the steel. It will fail at 75 kilonewton itself. The concrete will fail at 75 kilonewton itself. So the steel will get suddenly failure. So that is due to over reinforced section. And next one is shear failure. Shear, it is the breakdown of the section. So if the depth of the beam is not properly designed, or if the cross section of the beam is not properly designed, then it will fail under shear when the flexural strength reaches its maximum limit. Then failure of bond between the steel and surrounding concrete. So in this failure, so in first module itself we discussed high strength concrete and high strength steel is required in PSC. So especially in case of post tension, we are using, there will not be bonding at all between tendons and concrete, because after casting we are going to provide tendons. So to provide bonding, we are going to provide grouting. So the strength of grouting will be major role in the bond between concrete and grout, as well as grout and tendon. There will be two bondings should be proper. If the bonding is not proper, then the strength in the tensile zone, tendons will goes on decreases, and there may be chances of failure. Then anchorage failures. So after applying the tensile stress, we are going to hold the tendons in the position with the same tensile stresses. If we not designed those anchorage devices properly to hold the tendons in the position, and if the anchorage devices get fails, the tendon will come back to its original position, so there will be no tensile stresses in the tendons. So in that case, what happen, the upward deflection what we are going to provide by using pre-stressing force, that will not be there in the beam. So excess deflection will come in downward direction and the beam will get failure. So these are the different modes of failure under flexural strength. Then, so one more important question which we can face in the examination is IS code method of determining the ultimate moment of resistance of rectangular and flanged section. So here we will be having 4 different cases. One with rectangle bonded, rectangle unbonded, then flanged bonded, flanged unbonded. Based on the data given in the question, we need to follow the procedure. So first, for rectangle portion, we will be having this stress distribution diagram. Then there will be no question of neutral axis also. It will be lies in the section only. So XU less than DF, greater than DF. For rectangle section, the XU is less than DF only we are going to consider. Then if XU is greater than DF, then we are going to consider it as flanged section. So we have procedure. So first one is moment of resistance of pre-tension and post-tension bonded rectangular sections. So rectangle section with bonded tendons. So first we are going to calculate what is the effective reinforcement ratio we required. So for that we have formula APFB by BDFCK. The descriptions of these terms is given in IS 1343 and you can refer for the even procedure also. So first we need to find out effective reinforcement ratio. Here the effective reinforcement ratio is the ratio of area of steel provided to the area of cross section of the section with its characteristic strengths. Then for the next step is above reinforcement ratio, then FPU by 0.87 FB and XU by D ratio we need to find out, and by using IS 1343 code book we are going to calculate FPU and XU values. Then moment of resistance by using the formula M equals FPU AP into D minus 0.42 XU. So these are the 3 steps if the given problem is rectangle section with bonded. Next, moment of resistance of pre-tensioned or post-tensioned bonded flanged section. Here it may be I section or T section like that. In case of flanged sections, again the same steps, few additional steps will be there with some conditions. So first we need to find out effective reinforcement ratio. Then after effective reinforcement ratio we need to find out FPU and XU value by using IS 1343 code book. So after calculating or after finding the XU value, first we need to compare it with whether the neutral axis lies in the flange or in the web. If XU is less than DF, depth of the flange, then directly we will go for calculation of moment of resistance using the formula. If XU is less greater than DF, or if XU is lies in neutral axis lies in web, then area of steel in flanged section and area of steel in web section, those we need to find out. Then we need to find out what is the area of steel. First we need to find out what it is the area of steel in flange, by using the formula 0.45 FCK into B minus BW into DF by FP. After that, you need to find out what is the area of steel in web portion. Then again we need to find out for web portion what is the new effective reinforcement ratio. Again for new effective reinforcement ratio we need to find out FPU and XU. Then we need to find out moment of resistance using the formula. These formulas are available in codebook. So these two are for bonded condition, bonded rectangular and bonded flanged sections. So what if the given condition is unbonded sections, unbonded rectangle, or if it is unbonded flanged sections. So first let us go for bonded rectangular section. Again here also we need to find out effective reinforcement ratio, and additionally we need to find out L by D ratio. In case of unbonded, first we need to find out effective reinforcement ratio and L by D ratio, span to depth ratio. Then for the effective reinforcement ratio and L by D ratio, we calculated the values of FPU and XU are available in table 12 of IS 1343. So by referring that table number 12, we need to find out FPU and XU. Then moment of resistance using the formula. If the section given is unbonded flanged section, then first we need to check for depth. That is, first we need to find out effective reinforcement ratio and L by D ratio. For obtained effective reinforcement ratio and L by D ratio, we need to find out FPU and XU values. Then compare it with depth of flange. If the XU lies in the flange, directly we need to go for moment of resistance. If the XU is greater than DF or neutral axis lies in the web, then first we need to find out area of steel in flange. Then we need to find out area of steel in web, APF and APW. Then new effective reinforcement ratio with respect to web reinforcement and L by D ratio. Again we need to find out new FPU and XU value. Then at last we need to find out moment of resistance by using the formula. So this is about some theory part introduction with respect to flexural strength of members, and these are the two important theory questions you can expect in the exam. One is different modes of failures, and these four cases it may be given as discuss the procedure to calculate the moment of resistance in case of bonded flanged section or unbonded flanged section. Like this you can expect the questions on these topics. So in next class I will discuss with the problems, and thereby you can understand the procedures what I have explained here clearly. Thank you.